This video is for section 7.3 on sample means. So we're going to begin by talking about the mean and the standard deviation of the sampling distribution of X bar. Suppose that X bar is the mean of a simple random sample of size n drawn from a large population, and this large population has a particular mean, which we let be mu, and a standard deviation, which we let be sigma. Then the mean of the sampling distribution of X bar would be the mean sub X bar, so basically the mean of the sampling distribution, which is going to be equal to the mean of the population. The standard deviation of the sampling distribution of X bar is sigma sub X bar, which is equal to the standard deviation of the population over the square root of the size of the population, as long as the 10% condition is satisfied. And so it reminds you that the 10% condition just means that the size of the simple random sample is less than or equal to 1/10 of the entire population, which is the capital N. So let's look at an example. So sulfur compounds such as dimethyl sulfide, DMS, are sometimes present in wine. DMS causes off odors in wine, so winemakers want to know the odor threshold, the lowest concentration of DMS that human nose can detect. Extensive studies have shown that the DMS odor threshold of adults follows a roughly normal distribution, with a mean equal to 25 micrograms per liter and a standard deviation 7 micrograms per liter. Suppose we take a simple random sample of 10 adults and determine the mean odor threshold X bar for the individuals in the sample. So for A, what is the mean of the sampling distribution of the X bar, and explain. So we're finding the mean of the X bar. So since X bar is an unbiased estimator of the mean, then the mean for X bar would be equal to the mean for the entire population, which we know is 25. So the mean sub X bar would be equal to 25. And this means that the mean of the sampling distribution would be 25. All right, for B, what is the standard deviation of the sampling distribution of X bar? Check that the 10% condition is met. All right, so let's first check the 10% condition. So the 10% condition just means that the sampling distribution, or the simple random sample size, the little n, is less than or equal to 1/10 of the entire population. So what we want to know is, for one, we want to think about what our n is going to be, our little n. And so for this one, our little n is 10, because it says that we take a simple random sample of 10 adults. Now what that would mean is that our entire population would have to be at least 100. So that would mean that we would say like 10 times 10 would be equal to 100. So our n would have to be, our big N would have to be greater than or equal to 100 in order for this to hold. Now, because we are talking about adults in the population, we would say that there's definitely more than 100 adults, so we're good with the 10% rule. All right, so then we have to think about the standard deviation. So we're finding the standard deviation of X bar. And so we're going to use the formula, which we know is sigma over the square root of n. And so sigma represents the standard deviation for the entire population, which it tells us that our standard deviation of the entire population would be 7. So we would have 7 over the square root of our simple random sample, which is going to be 10. So 7 over the square root of 10. If you were to do that on a calculator, you would need to do alpha y equals so that you could get a fraction. On top of that fraction, you would put 7. On the bottom, you would put square root of 10. And you would see that you got 2.21359432. So we're going to round that to be about 2.214. Sampling distribution of a sample mean from a normal population. Suppose that a population is normally distributed with mean m and a standard deviation sigma. Then the sampling distribution of x bar has a normal distribution with a mean mu and a standard deviation sigma over the square root of n, provided that the 10% condition is met. Alright, so for the next example, we are going to be finding probabilities involving the sample mean. So for the problem, it says the height of young women follows a normal distribution with mean mu equal to 64.5 inches and a standard deviation sigma equal to 2.5 inches. A says find the probability that a randomly selected young woman is taller than 66.5 inches. Show your work. So for A, we're going to have to begin by finding or using a random variable. So we're going to let our random variable be x. And we're using a random variable because we are randomly going to be selecting a young woman. So we're going to let x be the height of a randomly selected young woman. All right, we already know that the mean for the population is 64.5 inches, and we know that the standard deviation is 2.5 inches. We're trying to find the probability that our x, our randomly selected young woman, is greater than 66.5. So the height of a randomly selected young woman is greater than 66.5. Now, of course, you can standardize this and get a z-score and use the table for this, but you can also do it on the calculator by using normal CDF, where your lower bound is 66.5, because remember, we want to be greater than 66.5, and our upper bound can be 9e99 or infinity, however you want it to represent that on your calculator. Your mean is 64.5 and your standard deviation is 2.5. So whenever you go to do this on the calculator, you would need to go to second vars, go to option 2, lower bound is going to be 66.5, upper bound 9e99, and your mean is 64.5, and your standard deviation is 2.5. And whenever you do that, you get 0.211, essentially 9. So 0.2119. If you wanted to do this on the table and you wanted to standardize, then you would need to get your z-score. So you would say 66.5 because that's your observation. Subtract your mean over your standard deviation. Whenever you do that, you would get 0.80. And if you were to look on the table at 0.80, you would find that it's 0.7881. But because you're finding the probability that a randomly selected, or the height of a randomly selected woman is over 66.5, that means that you are going to be finding the probability that z is greater than 0.80, because the 0.80 is what goes with that 66.5. Because we are looking at greater than, z greater than, we would need to do 1 minus whatever our 0.80 is. And so we said that that was 0.7881, and whenever you do that, you get 0.2119. So either way, you're going to get the correct answer. It's just two different ways that you can do it. Remember, on the AP exam, though, they are going to kind of frown upon you doing the normal CDF and using that as your steps, especially on those free response questions and your investigative task, your question 6. And so you want to make sure that you are aware of how to do it using the normal table. All right, for B, find the probability that the mean height of a simple random sample of 10 young women exceeds 66.5. All right, so for this one, the sampling distribution of their sample mean height will have a mean, which would be equal to the population mean, which is 64.5. We also need to check and make sure that the 10% condition is met, since there has to be at least 100 women. And so if we think about this, we have 10 that we are looking at, and of course there are more than 100 young women in the population, so our 10% condition is met. Our standard deviation for X bar would be equal to standard deviation for the population over the square root of our simple random sample, and so that would be 2.5 over the square root of 10. Whenever you work that out, you get 0.79. Since the population is normal, or population distribution is normal, the values of X bar will follow a normal distribution with a mean of 64.5 and a standard deviation of 0.74. So then if we want to find the probability that X bar is greater than 66.5, we could standardize that, of course, like we did up here. We could also do normal CDF, so I'll show you how to do that. So your normal CDF, you would let your lower bound be the 66.5, your upper bound be infinity, however you want to represent that. This time your mean is going to be 64.5, but your standard deviation is going to be 0.79. So when you go to do that on the calculator, you'll do second bars. You'll do option 2, normal CDF. Your lower bound 66.5, upper bound infinity. Mean stays at 64.5, but your standard deviation changes to 0.79. And whenever you do that, you get 0.005, approximately 7. Again, like I said before, it's always helpful to know how to do it using the Z table, or using a Z-score and using the standard normal table. So you would get 66.5 minus 64.5 over your standard deviation, which is 0.79. Whenever you work that out, you would get 2.53. And so then, because you're finding the probability your X bar is greater than 66.5, that means that you're really finding on the standard normal table the probability that your Z is greater than 2.53. So because it's a greater than, you're going to say 1 minus whatever 2.53 gives you on the normal table, and that would be 0.9943 if you're to look it up. Whenever you work that out, you would get 0.0057, which is what we got up here. So remember that 2 ways to do those. Always good to know how to do it on the calculator because it's an easy, fast way, and it's great, especially on the multiple choice. Always good to know how to do it on using the standard normal table, because that's kind of what they look for on your free response questions. So, check your understanding. The length of human pregnancies from conception to birth varies according to a distribution that is approximately normal, with a mean of 266 days and a standard deviation of 16 days. Number 1 asks us to find the probability that a randomly chosen pregnant woman has a pregnancy that lasts for more than 270 days. Show your work. It also asks us to suppose that we choose a simple random sample of 6 pregnant women, and we're going to let X bar equal the mean pregnancy length for the sample. So essentially on number 1, what we're finding is the probability that X, where X is equal to a randomly chosen pregnant woman. And this X really represents the length of the pregnancy. So we might say pregnancy length of a randomly chosen pregnant woman. So our X, we want to know what is the probability that it's greater than 270. So again, you can always get your z-score and do it that way. Or you can do normal CDF. So for this one, let's do normal CDF. Your lower bound 270, your upper bound 9E99, your mean 266, and your standard deviation 16. So second VARS, option 2, lower bound 270, upper bound 9E99, your mean 266, your standard deviation 16, and when you work that out, you get 0.4013. Of course, again, you can do it with the z-score. Whenever you do that, you would be looking for the probability when z was greater than 0.25. I got the 0.25 by doing 270 minus 266 over 16, and so that's how you get the 0.25. Whenever you work that out, you would get exactly the same answer. 2, what is the mean of the sampling distribution of X bar? And explain. All right, so the mean of the sampling distribution of X bar is actually going to be equal to the mean of the distribution of X, X being the pregnancy length of a randomly chosen pregnant woman. And so it tells us up in the problem that we are looking at an approximately normal distribution with a mean of 266. So our mean would be 266. 3 asks us to compute the standard deviation of the sampling distribution of X bar and check that the 10% condition is met. Alright, so it tells us that we are going to choose a simple random sample of 6 pregnant women. So remember that the 10% condition means that our sample that we choose has to be less than or equal to 1/10 of the entire population. And so our N is 6, which means that we essentially need 6 times 10 to be what our N has to be. Our capital N, our population, has to be greater than or equal to. And so that means that we have to have an entire population that's greater than or equal to 60. Actually, I have that backwards. So we definitely have more than 60 pregnant women in the world, so we are good to go. Okay, next thing we're going to do is find the standard deviation. So we're finding the standard deviation for X bar. And so we're going to use the standard deviation for X over the square root of the population that the sample that we're looking at. And so our standard deviation in our problem up here tells us that it was 16. And we know that we are taking a simple random sample of 6. So we're doing 6 over the square root of 16, which when you work that out gives you 6.32 days. Number 4 asks us to find the probability that the mean pregnancy length for women in the sample exceeds 270 and show our work. So we are finding the probability that X bar is greater than 270. So we can do the z-score thing. If we do that, we would be saying 270 minus 266 over 6.532. And whenever you do that, you would get 0.61. So we would be finding the probability that our z was greater than 0.61. We can also do this on the calculator using normal CDF. And so if we do that, our lower bound is going to be 270, our upper bound, infinity, our mean, 266, and our standard deviation, 6.532. So on the calculator, second var's, option 2, lower bound is 270, upper bound 98.99, mean 266, and standard deviation 6.523. Actually, it's 0.32. Not going to make a huge difference, but just for sake. All right. When you do that, you get 0.2701. If you were to do it using the standard normal table, you will get 0.2709, but those are pretty close to each other, so either way you get something that's pretty similar. One answer is not better than the other. All right, moving on to the central limit theorem, which you will often see abbreviated CLT. So what that means is when your sample N is large, the sampling distribution or the sample mean X bar is approximately normal. So normal condition for sample means if a population distribution is normal, then so is the sampling distribution of X bar. This is true no matter what the sample size N is. If the population distribution is not normal, the central limit theorem tells us that the sampling distribution of X bar will be approximately normal in most cases if your sample size that you're looking at is greater than or equal to 30. So an example, your company has a contract to perform preventive maintenance on thousands of air conditioning units in a large city. Based on service records from the past year, the time and hours that a technician requires to complete the work follows the distribution whose density curve is shown in the margin. You guys don't see that, but it looks kind of like this. This distribution is strongly right skewed, and the most likely outcomes are close to 0. The mean time is mu equal to 1 hour, and the standard deviation is sigma equal to 1 hour. In the coming week, your company will service a simple random sample of 70 air conditioning units in the city. You plan to budget an average of 1.1 hours per unit for a technician to complete the work. Will this be enough? Follow the 4-step process. All right, so remember the 4-step process is state, plan, do, and conclude. So to state, you're going to state what is your question that you are answering. So your question is, what is the probability that the average maintenance time which you know is X bar, for 70 units exceeds 1.1 hours. Your plan. So the sampling distribution of sample mean time X bar spent on 70 units has a mean, which is equal to the population mean, which is 1 hour. Your standard deviation for X bar is going to be equal to the population standard deviation over the square root of your simple random sample. So that's going to be 1 over the square root of 70, because you're looking at 70 units. And whenever you do that, you should get 0.12. You also want to check and make sure that the 10% condition is met. So you want to say that there are more than 10 times 70 or 700 air conditioning units in the population. So you're talking about a large city, you're definitely probably going to have more than 700 air conditioning units in the population, so you're good to go. Alright, so the next thing that you want to do is you want to check and make sure that you have an approximately normal shape. And so to do that, you're going to say, is my population that I'm looking at, which is 70, greater than or equal to 30? And because that works, then you do have an approximately normal shape. And the distribution of X bar is therefore approximately normal with a mean of 1 and a standard deviation of 0.12. And we want to find what is the probability that X bar is greater than 1.1. The next thing you have to do is do. So what you're going to do is you're going to find what is the probability X bar is greater than 1.1. And so you can use normal CDF. You can also standardize and use the normal table. So if you're using normal CDF, your lower bound is going to be 1.1. Your upper bound is going to be infinity. Your mean 1 and your standard deviation 0.12. On the calculator, second vars, option 2, lower bound 1.1, upper bound infinity. Mean is 1, standard deviation is 0.12. Whenever you do that, you get 0.2033. If you were to standardize this, you would find that your z-score would be 0.83. So you would get that by saying 1.1 minus 1 over 0.12. And so you would be finding the probability that z was greater than 0.83. Because it's greater than, you'd say 1 minus whatever 0.83 gave you on the table, which in this case would be 0.7967. And whenever you work that out, you would get the 0.2033, like I got up here by using the calculator. And the last thing that you have to do is conclude. So conclude basically your answer to the question that you stated up above. So if you budget $1.1 hours per unit, there is a 20% chance, so we get 20% by rounding this off and jumping over our decimal and getting 20%. So there's a 20% chance that the technicians will not complete the work in the budgeted time. And basically, you will have to decide if this risk is worth taking, or if you should schedule more time for the work.